Episode 6 of the World of FPGA podcast. After the last basic episode, we will dive deeper today and look into different specialties of FPGAs. Welcome to the World of FPGA podcast. I'm your host, David Kirchner, and I will lead you through the world of FPGA. And now, let's begin. In the last episode, we had many basics about FPGAs, and here is a short conclusion. We talked about the logic cells inside the FPGA, about the connecting cells and routing matrices. They are belonging to the logic cells and they are doing all the connections. We have the clock network, which delivers the clock for all our flip-flops inside the FPGA. We have some storage elements like RAM, configurable RAM. We have computing cells to doing some multiplication and addition. And we have connection to the outside world. This is more or less the basic inside an FPGA. And now I have some specialties which you found not in all FPGAs, but in the most FPGAs today. First, we have the clock generation. Yes, we talked last time about clocking networks. So we have networks which deliver the clock to our flip-flops, but we need something that generates or modifies the incoming clock signal or a local clock signal. So we have slow and we have fast elements inside these clock generations. And the first one I would like to talk are PLLs together with VCOs, so voltage controlled oscillators. PLLs are phase locked loops. This is some classic elements also outside of the world of FPGAs we are using to generate clocks from a fixed input clock, maybe 10 megahertz or 25 or 100 megahertz. And with the PLL together with the VCO, we can generate, not every clock, but many clocks, many stable clocks, which are phase locked. So the phase of the reference clock and the output of the clock there's a phase is locked. So we have defined clock signal, and with this we can generate many different clocks inside the FPGA. Not only slower ones, we can also generate faster ones, because these VCOs in these FPGAs are in a range of many hundred megahertz to gigahertz. And there's also in the most chips a digital clock manager, which can be configured to have different output phases, for example, or different output frequencies from a main frequency. Maybe we have 800 megahertz generated in the VCO. Then we can use the clock management to generate clocks with a division of 2, 3, 4, 5, and so on, to get slower clocks inside for our inside logic in the FPGA. Some of the FPGAs has oscillators included on the chip, so we can use these oscillators to generate a local clock signal without an external reference clock. That's also very nice to have small designs. Sometimes you need two different reference signals from the outside world. So it is possible to have clock switches. There are special switches which switch from one clock, maybe from a faster to a slower clock, and avoid glitches. So we have the fast signal, and if we switch, we have some faster signals, some glitches, and then the next clock signal comes. We can also use this. We can use this clock switches to switch from the fast clock, and if maybe the rising edge is reached from a fast clock, then the clock switch will switch to another clock in that moment when the falling edge is coming. So we have no glitch. We have maybe a short pulse with this with a higher width with respect to the two clock signals, but we have no glitches, and this is very important to have a good clock signal inside our FPGA. And many FPGAs have also low power modes, so we can slow down our logic if we do not need it, or we can stop the logic if we do not need this. Maybe we have some applications to use this. The next element are SERDES. SERDES is the abbreviation or the combination of serializer, deserializer, and they are found often in FPGAs, always as some kind of hard IP, so as a block which is not generated in the FPGA logic. It is also on the silicon, but in an extra area on the chip. And it is used for high-speed connections. It's very high speed because we can have speeds up to several tens, several hundreds gigabits per second. Normally we find in mid-range FPGAs we find 5 to 10 gigabit for this serial connection, and most time they are differential. Sometimes we have some they are differential, no single-ended, and the connection is serial. So we have only one differential pair for our communication, and then it goes into the deserializer and gets into parallel words, which are very not very slow, but much slower than our high-speed connection. On the other hand, if we want to send data, we have our parallel data word, 8-bit, 32 bits, could be very big, and this will go through the serializer and go out of the chip with a high-speed differential signal. It's often possible to use multiple lanes, so we have not one serial connection to the outside world. We have, for example, 4 or 8 connections to the outside, and so we can multiply our bandwidth here. And there are many integrated support like 8-bit, 10-bit coding and decoding to have some support for our system. We can also have some word alignment, so we are receiving the information and can say where starts our word and where ended, and we always get the correct word out of the deserializer. And we have also a technique, it's called clock recovery. So we get a signal, and from the signal, which should have some special configuration, the deserializer can also do some clock recovery and also some also divides the clock speed down to the speed of the words, so we can use directly this clock signal inside in our logic. The next block is MIPI, is a MIPI connection to the outside world, or also from the outside to the inside. The interesting thing here is some FPGAs have hard IPs for that. In some FPGAs you need your own logic to receive or to send such kind of signals. In the hard IP version, we always have high speed and low power modes integrated with all the electrical things we need for this kind of signal, because low power mode is low speed, but full range at high speed is a more differential signal with the higher frequency. And these MIPI blocks also support us with word alignment things and also have integrated serializer, deserializer. Another possible block inside an FPGA can be a processor. So we have, for example, an ARM core we can use inside our FPGA. Often there are hard IP, but we can also generate a soft IP CPU, for example, a RISC-V processor, or we can use GPUs, or we can have other kinds of additional things. For example, interfaces we can generate for our processor inside our logic, a UART, an SPI, an I2C, and other things we want to use with our processor inside our inside our FPGA logic. Some special things are SoCs, so system on a chip. There we have one part with our programmable logic. Another part is a CPU. And then the CPU has often many interfaces that bring us connection to the outside world. For example, some Ethernet connection, some UART, some SPI, USB, and all the things. And also memory controller is often integrated. And the last point, which is very interesting on some FPGAs, is partial reconfiguration. Yeah, the FPGA is a master in this thing because we have a defined logic. And the idea behind partial reconfiguration is we can use this for change a block inside our FPGA logic while we are using the FPGA. We do only reconfigure one block inside of our logic from an external memory. And important here is we have to define an area where this block will be, and we have to define interfaces. So we can take out the old block, put the new block inside, and we have the same points we receive our data, and we send out our data, and where we get our clock signal and so on. So we cannot change the routing of the FPGA in real time. We just reconfigure, for example, the lookup tables and connection cells inside of this partial reconfiguration block. This is a funny thing because we can exchange the function of a block during operation, during using our FPGA. That's for the end, just a funny thing we can use. So that's all for today's episode. I hope you know now a little bit more about FPGAs. In the next episode, we will discuss programming languages. And now, a last but very important information, the World of FPGA platform is opening. Just follow us in LinkedIn. You can have a look into the show notes, or you search in LinkedIn for World of FPGA. The launch phase will begin on Sunday, and it would be awesome if you would share this LinkedIn posts to other people and into your own timeline to support us. And if you hear this much later, then just visit my learning platform anyway, and step in a little bit later. We have always open. Yeah, all links and further information can be found at world-of-fpga.com/WFP006. If you found this episode helpful, please rate it on Apple Podcasts and share it with your colleagues and friends. That's the end of today's podcast episode. Thank you for listening and for your attention. So I say goodbye, here next time, your David Kirchner.